Good evening. I'm Alexander Rose. I'm the Executive Director here at the Long Now Foundation, and I'm going to be hosting and doing the Q&A for this evening. It's both lucky on my part because Marcia was a suggestion of both mine and board member Paul Safo's. I think we both had the experience of reading this book and kind of dog-earing page after page after page and realizing how important it was to bring her to this audience. Kind of her insights in this book really are some of the very same things that instigated Long Now at the beginning. As many of you know, we start these talks with what's called a long short, a short film about long-term thinking. And I think as in a first, we have a long short that was created by Finn, Marcia's son, with her for this talk. So enjoy. And as I mentioned, this is one of those books as I was reading it, I realized more and more how it was so in line with Long Now's very origins, in that literally this idea of timefulness that Marcia writes about is very literally the concept of lengthening our now. And I think one of my favorite things about talking with astronomers and geologists is they're the only people who make our 10,000-year time frame seem positively tiny and quaint. But I think she does it in a way that is very human-centric, and so I'm very excited to hear from Marcia Bjornerud this evening. Thank you.
Thank you, Xander and Danielle and Andrew and all the others who have made my visit here so wonderful. Well, I'm not sure how common an experience it is for Californians, but for children who grow up in a wintry climate, few events in life will ever deliver the same pure joy as a snow day. Time is temporarily repealed, the oppressive schedules of the adult world magically suspended in a concession to the greater authority of nature. I recall one particular snow day when I was growing up in rural Wisconsin in the 1970s. There'd been a ferocious blizzard in the night with heavy snow and high winds that by morning had brought bitter cold. But I couldn't resist going out to survey the transformed world. Trees creaked and groaned as they do when it is especially cold. I spotted a dab of red on a branch and saw that it was a cardinal. I started walking toward it in the heavy snow and was surprised when it didn't move. I got closer still and then realized with both revulsion and fascination that it was frozen on the branch. It was as if time itself had been frozen, and I was able to witness something that was normally a blur of motion. Back in the house later the same day, I remember heaving our unwieldy world atlas down off the shelf, where I remember it sat right next to the whole Earth catalog, and paging through it. I came to a map of time zones around the world with the globe divided mostly into longitudinal stripes of alternating color. But there were several places, Antarctica, Outer Mongolia, and one I'd never heard of, Svalbard, high in the Arctic, that were colored gray. The legend said these places had no official time. I was captivated by the idea of enclaves that had somehow resisted being shackled by measures of time, no minutes or hours, wholly exempt from the tyranny of a schedule. Was time there frozen like the cardinal on a branch, or simply flowing, unmetered and unfettered according to a wilder natural rhythm? My next encounter with Svalbard happened a few years later at an exhibit of Scandinavian photography at the Minneapolis Institute of Art. Most of the pieces were predictably moody, modern Nordic works, but my attention was caught by several haunting images of the ill-fated Eagle expedition, an 1897 attempt by 3 Swedes to fly over the North Pole in a hot air balloon. Within days of its launch, the balloon went off course and crashed on the sea ice off one of the most bleak and remote islands in the Svalbard archipelago. No one knew, however, what had happened to the expedition until more than 30 years later, when the wreckage was discovered and film that was still in the cameras at the site was developed, silently documenting the disaster and the slow demise of the explorers. This only reaffirmed my conviction that this place, Svalbard, was somehow timeless, outside time. As it happened, I would end up doing my PhD research in Svalbard, and later spent additional summer field seasons there as a geologist working with the Norwegian Polar Institute. I quickly learned that the no official time designation was nothing as romantic as I had imagined, but instead the result of a long-running political spat between the Norwegians and Russians about whether to use Oslo or Moscow time there. And I began to understand that the place was not timeless, but in fact timeful. When I first arrived there in the 1980s, it still felt like the Pleistocene, the Ice Age. The place was still firmly in the grip of ice. Artifacts from the last few centuries of human activity were strewn sparsely across the vast landscape, as if in a poorly curated museum display. There were whale bones scattered on the tundra, remnants from 17th century Dutch blubber rendering. There were 18th century Russian graves from the time of Catherine the Great, when exile to Svalbard was a slow death penalty. There were huts built of driftwood by 19th century miners and hunters with old boots in the corner and rusty tin cans still on the shelves. And there was the sinister wreckage of a Luftwaffe plane, untouched since the 1940s, a profane and malign presence in that beautifully austere landscape. Somehow, all these past times signified by these objects seemed equally close, all still palpably present. My field research focused on understanding the tectonic evolution of the northernmost part of the Appalachian Caledonian mountain belt. And immersed in this work in a place so remote from modern life, I began to feel that this 400-million-year-old event and the still older rocks recording it were more proximal in time than the 20th century world. In places like Svalbard, with comparatively little human clutter, it's easy to sense the presence of the past. But everywhere, the natural world is bursting with backstories. The world is made of, or more precisely, by time. This is what I mean by timefulness, an awareness of the rich natural history that envelops us, a sense that we too live in geologic time and are part of a continuum from the planet's past into its future. Timefulness is a deliberate counterpoint to timelessness, an unattainable, sterile, and, I will argue, even dangerous idea. But we live in a time-illiterate society, as I don't need to tell this audience. We would be shocked if an educated adult had no idea where the continents were on a global map, but don't seem bothered by the fact that few average people have a good sense of the geography of the planet's past. Even though we will spend our entire lives here, we behave like bad tourists on Earth, enjoying its amenities and ransacking its bounty without ever having noticed that it has its own ancient language and customs. Many of the environmental problems we face have arisen because we collectively lack a sense for the duration of chapters in Earth's history, the rates of geologic processes like groundwater flow, or the intrinsic timescales of natural phenomena like climate change. I suspect that you Californians with the San Andreas and related faults just beneath your feet might be more in tune with the planet's rhythms than the average Earthling. But in our culture, time denial, or what we might call Chrono Phobia, is rampant and comes in many varieties arising from different sources. The most obvious and vocal is, of course, young Earth creationism, but it's worth noting that 200 years ago, geology and theology were really not at odds. And in fact, the scientific discovery of deep time, to use John McPhee's evocative phrase, was actually motivated by religious belief. The beginning of modern geology as a discipline is usually traced to a Scotsman, James Hutton, who was a physician, gentleman farmer, naturalist, and polymath on the fringes of the Edinburgh Enlightenment. He often drank and dined with the likes of the philosopher David Hume, the inventor James Watt, economist Adam Smith, and apparently Ben Franklin even visited him once. As a landowner, Hutton was concerned, for economic reasons, at the large amount of soil he could see was being washed away to the sea every year. As a religious person, a deist, like many Enlightenment thinkers, he was also troubled spiritually by the idea that God would simply allow the earth to be worn steadily away, that sometime in the future all of the continents would be eroded to sea level, and that the earth would be uninhabitable by humans. His writing suggests that he was actively looking for evidence of some compensatory process of rejuvenation, and he found it late in his life at this rocky promontory off the coast of Scotland, Sicker Point, the east coast. So what we see are two sequences of rocks, an underlying sequence in which the beds are nearly vertical, and then a second sequence of rocks partly overlapping that vertical sequence that are almost horizontal, but in fact slightly tilted. And here's an illustration from my book, and I should mention that the illustrations in the book are done by a former student of mine who impressed me with her fossil sketches in an intro geology class. So here's a rendition that's a little simpler to understand of these two sequences of rock. Hutton, back in 1788, made the great intuitive interpretation that the older sequence of rocks tilted on end represented the vestiges of an ancient mountain belt. And the contact between these two sequences of rocks represented the time it would take to erode a mountain belt back to sea level and then have a succeeding sequence of rocks deposited on top. And so he recognized that surely the 6,000 or so years that was allotted by a literal reading of the Bible was certainly not enough time to erode a mountain belt to the sea. Hutton made an even greater inductive leap and surmised that the rocks at Sicker Point recorded just one of countless cycles of uplift erosion over the history of the Earth. His 1788 treatise, Theory of the Earth, published the year before he died, famously ends with the sentence, "The result, therefore, of our present enquiry is that we find no vestige of a beginning, no prospect of an end." So Hutton gave us great deep time, but he wasn't particularly interested in any granular details of what precisely happened during those vast eons. Hutton's beautiful idea of an Earth that was infinitely old and continuously regenerating captured the public imagination in the way that space exploration does in our time. This is a depiction of Hutton's unconformity from 1802, it was actually 3 years after he died, that was widely circulated in Britain and the US and ignited public interest in the emerging science of geology. And again, you can see the vertical sequence of rocks, a kind of rubbly layer, and then the succeeding sequence, and then the modern layer on top. This image and the ideas behind it did not seem to have raised the hackles of the clergy. I'm not a scholar of religious history, but to me this suggests that in that era, the timescales of Genesis were generally accepted as metaphor rather than literal truth. It wasn't really until paleontology began to uncover evidence of extinct creatures and vanished ecosystems, and then when Darwin, of course, suggested how organisms, including humans, could have evolved through the non-directed process of natural selection, that the church began to see geology as a threat. I want to acknowledge that many other cultures around the world probably did not have the same aversion to deep time and the idea of biological evolution that the Judeo-Christian West has had, but I focus here on the European tradition because it is, in fact, where modern geology and the calibration of deep time got its start. Anyway, at this point in the 21st century, geology has been contending with creationists and young earthers for more than 150 years. And it's easy to be derisive about young earth thinking, but I do empathize with people who are truly struggling to reconcile their religious beliefs with scientific understanding. Cognitive dissonance hurts. I occasionally have students who are in this position, and I offer them a variation on an argument made by Descartes in his Meditations on the Nature of Reality. Early in an intro geo class, one begins to understand that rocks are not nouns, but verbs, records of processes. This limestone signifies the accretion of a coral reef. That garnet schist represents the growth of a mountain belt. So I asked these students to consider which is more heretical, to accept the idea of an old and evolving Earth set in motion 4.5 billion years ago, whose internally consistent history, a remarkable, awe-inspiring saga, has been worked out little by little over the past 2 centuries by people from many cultures, or a deceitful creator who has planted false clues about the planet's past in every nook and cranny, from fossil beds to zircon crystals we may one day analyze just to mislead us deliberately. I let students decide for themselves. But I have no patience for the aggressive misinformation, the awful mashup of biblical literalism with alleged science that is posted online by the Institute for Creation Research and turned into lucrative business ventures at places like the Creation Museum in Kentucky. To those who actively distort scientific facts and fog the brains of young earthlings, not to be confused with young earthers, I would say, okay, then live with the consequences of your worldview. You won't have access to fossil fuels, since the gas in your car was found by geologists with an understanding of the stratigraphic record. Likewise, modern medicine is off limits, since it's based on testing on mice, which only makes sense if you understand that they are our evolutionary kin. Apocalypticism is a dangerous offshoot of religiously motivated time denial, in which not only the geologic past, but the future are foreshortened. If you think there's no future, then there's no need to conserve or be concerned with climate change. In fact, not using up resources is paradoxically wasteful. But again, young earthers are at least completely open about their aversion to time. More insidious forms of time denial are woven into the fabric of our culture. Our natural existential dread of aging and death has become entangled with vanity through capitalistic messaging in a society obsessed with youth. As a result, we fear and loathe our timiness. Making us afraid of time is big business. Time denial is a multi-billion-dollar industry. At least this product seems to be completely forthright about being utterly detached from reality. Have you noticed these days we more often refer to ourselves as consumers rather than citizens, and that doesn't really bother anyone? Citizen implies living somewhere over time in proximity to others with the attendant give and take that requires. Consumer suggests only taking, as if our sole purpose were to devour everything in sight now in the manner of locusts descending on a field of grain, with no thought of the consequences for the future. And we are as insatiable as locusts for novelty, the newest smartphone, the just released app, the meme of the moment, the latest elixir of life. We don't notice how quickly all of these age, become old, tired, so 5 minutes ago, because the next ones arrive to take their place before we've had a chance to dwell on that, allowing us to remain pleasantly distracted in a never-ending now. This narcissistic preoccupation with our own creations has led to a mass illusion that we've outgrown the natural world. In this country in particular, there's a widely accepted notion, a virtual credo, that free markets represent an almost sacred natural state, that anything that fetters them, including protections for nature itself, which produces the raw goods for the never-satisfying economic monster, is unnatural. And while we may scoff at apocalyptic thinking, the opposite view, that we can carry on forever at increasing levels of resource consumption, is equally diluted. In 2016, the novelist Amitav Ghosh published this provocative series of essays, originally written as a lecture series at the University of Chicago, in which he makes the point that so far literary fiction has failed to address climate change, the central issue of our time. He reminds us that literature has often anticipated and catalyzed revolutions in human society, from ending slavery and regulating meatpacking even. But he argues, few serious novelists have yet found a way to write compellingly about impending changes in the natural world. I would say that in just the last year or so, several prominent writers have risen to this challenge. For example, Louise Erdrich in The Future Home of the Living God, and Richard Powers in The Overstory. Still, I think Ghosh articulates an important idea, that we in the West have little appetite for stories without individual human protagonists, and that is essential if we are to take action on global environmental challenges. The title has two meanings: the derangement we have caused to nature, and the derangement in our belief that we are outside the narrative of nature. And here is where science, and geology in particular, can help by doing a better job of telling the remarkable stories of the natural world. Tolstoyan in the number of characters. These come in all genres, some heartwarming, some terrifying, some cryptic, some stranger than fiction. But it must also be acknowledged that science itself is culpable for subtle strains of time denial. In the hierarchy of sciences, it's telling that the pure, that is the timeless, eternal ones, physics, but also chemistry, are most esteemed, while biology and geology, which positively reek of time and history, are by implication impure. There's no Nobel Prize in geology, though there is one in economics. I respect the accomplishments of other sciences. Geology is, in fact, a very interdisciplinary field that necessarily draws on the principles and methods of physics, chemistry, and biology. But many environmental problems we face are the result of the failure in the early to mid-20th century to anticipate how new technologies, the internal combustion engine, chemical fertilizers, antibiotics, plastics, would interact over time with complex, evolving natural systems. The scientists and engineers behind these innovations could have used a bit of geologic thinking, timefulness. An unfortunate reality is that the unintentional consequences of our technologies will almost always outlive our intentional implementation of them. To think geologically is not as much about time itself as the power of time to inexorably alter, entangle, magnify, ramify, and otherwise complicate. But geology, too, as a discipline, has been at fault for failing to put human and planetary timescales in proper perspective. First, for a variety of reasons, geology is a late bloomer. It's a bit embarrassing to note that the laws of thermodynamics were worked out in the 19th century, the structure of the atom in the early 20th, but plate tectonics, the way the solid Earth works, was not figured out until 1965. Some of the delay was technological. Earth was just too close and too big to see clearly before that time. But it was also partly due to the myopia and lack of imagination of the majority of geologists in the early to mid-20th century who were too preoccupied with locating coal, oil, and mineral resources to recognize the clear evidence that Earth is a dynamic planet that was continuously reconfiguring itself. Another ironic reason for public time illiteracy is that in some ways geologists have been too emphatic about the immense antiquity of the Earth and slowness of geologic processes as a result of our constant vigilance against young Earthers. I'm sure you're all familiar with the 24-hour clock analogy for geologic time. If the 4.5 billion year history of Earth were condensed into a 24-hour period, modern humans would emerge at just the last fraction of a second before midnight. But I think this is really a wrong-headed depiction in several ways. First, it's alienating. It suggests we appeared out of nowhere and denies our deep roots in the evolutionary past. Yes, we humans in present form are relatively recent arrivals, but our ancestors have been here since the early morning hours. And it seems to absolve us from responsibility for our actions. How could anything we've done in that last fraction of a second matter to the Earth? Also, as those of you who live in a tectonically and geologically active area know, Earth is really not so sluggish. It has many tempos, moods, and modes, sometimes too fast for us to keep up with. And there are unfortunate asymmetries in the rates of processes. Evolution is slow, but extinctions can be brutally sudden. Sliding into an ice age is generally gradual, but warming up is often abrupt. Groundwater accumulates for centuries or millennia, but can be depleted in decades. Finally, another reason that geologic thinking has not made inroads into public discourse is that the field, frankly, has a PR problem. For many people, it either evokes musty museums, it seems to be a about a dim and irrelevant past, or about rapacious resource extraction. In most of the country, and California may again be an exception, there are no rigorous, engaging courses in modern geoscience in most high schools, so few people are aware of the field as a distinct discipline. And that's one reason that many geologists, including me, came into the field almost by accident. I do recall as a first grader having a fascination with Surtsey, a new island formed off the coast of Iceland in the 1960s. In school, we watched a movie showing the spires of steam and hot ash shooting out of the cold North Atlantic. It suggested a secret life force inside the stony-faced earth that terrified and thrilled me. But no one said, people called geologists study such things. And 10 subsequent years of uninspired school science and not one female mentor drummed out of me any nascent thought of becoming a scientist. As a freshman in college, I signed up for geology almost on a whim. My expectations were low. Everybody called it rocks for jocks. I found that it was a different kind of science that required a type of whole brain thinking I hadn't encountered before. It demanded a humanities-like close reading of the texts of the natural world. It involved the rigorous application of physics and chemistry to wild and unruly things like volcanoes and oceans. And above all, it required a vivid but disciplined imagination, the capacity for visualization across great expanses of time and space. And I saw its vast explanatory power. It was nothing less than the etymology of the whole world. Geology is a strange hybrid of the pragmatic and the philosophical. It's about where to find oil and groundwater, how to protect people from natural hazards, but also about deep existential matters. Where do we come from? Why is the Earth the way it is? What factors favor stable, resilient ecosystems and societies? And it's as much about the future as the past. An apt metaphor for geologic thinking is that of a palimpsest manuscript like this one. In medieval times, texts written on parchment, a commodity that required a lot of labor to produce, were often scraped off and reused multiple times. But always vestiges of the earlier texts remained. Similarly, landscapes have their histories written all over them, scraped by erosion and overwritten many times. Once you become attuned to these earlier scribblings, it's impossible not to see them. I often feel like I don't just live in Wisconsin, but in many Wisconsins. There are forests still recovering from 19th century clearcutting. There are the Great Lakes and mighty rivers that governed ancient trade routes long before Europeans arrived, legacies themselves of the immense ice lobes that flowed down from Canada. There are the golden Cambrian sandstones marking the shores of long-vanished seas, and in the north, contorted gneisses that are the surviving roots of Proterozoic mountains. But every place on Earth has similar stories, sprawling million-generation sagas of stability and upheaval, seas rolling in and out, glaciers advancing and retreating, mountains rising and being erased by erosion. Reconstructing Earth's past from the raw rock record is truly one of humanity's great intellectual achievements, but it's underappreciated because it wasn't done by a solitary genius, but instead built up incrementally by casts of thousands over the last 2 centuries. It's truly astonishing that we've been able to retrieve so much information in such detail about most of Earth's biography. But the geologic timescale is still a work in progress. There's plenty for future generations of geoscientists to decipher. I recognize that some people feel diminished by geologic time, that humans are made insignificant by it, and I can understand that. I think it helps to start developing some depth of field in thinking about time. I had a math teacher who was fond of saying there are many sizes and shapes of infinity. And while geologic time is not infinite, it is long. Some past events, like the Pleistocene, the Ice Age, happened just the other day. Others say the formation of Pangaea a while ago, and some, the origin of life, for instance, a long time back. It's also useful to adopt the Greek distinction between chronos, raw time, billions and billions of years, and kairos, which is time within a narrative. As one starts knowing Earth's story, and those vast stretches of geologic time are filled with narratives, protagonists, and plot lines, it's no longer alienating. The characters become familiar, the themes resonant. Once we open a few volumes in the library of deep time, we can begin to recognize ourselves in the tales of earlier Earthlings. Indeed, I find the idea of a 7,000 or 8,000-year-old Earth with a shallow, short history positively terrifying. While the enveloping presence of so many ancestors with such a rich anthology of life stories to share is, to me, deeply comforting. So let me describe 3 salient lessons from the rock record that our ancestors have to share with us about surviving over the long term. First, worship the sun. The earliest records we have of life, fossilized algal mats called stromatolites, like these still living in Shark Bay, Australia, as well as certain geochemical traces of microbial activity, point to photosynthesis as one of the earliest strategies for nourishment. And although we've discovered a few ecosystems that seem to be entirely independent from the sun, living off chemical energy from deep sea vents, and in some cases directly off rocks deep underground, even many of these species seem to have descended from sun-loving ancestors. Love of the sun, what might be called heliophilia, is quite natural. Earth and life are both children of the sun. The Earth, an incidental byproduct of the sun's formation, does generate its own internal heat by radioactive decay, these days as a middle-aged planet, at a rate of around 30 terawatts. That's enough to power the global plate tectonic system. But this is far outstripped by the energy coming to Earth from the sun, about 200,000 terawatts, nearly 10,000 times more than what leaks out of the planet's interior. The sun's energy drives the water cycle, weather and winds, and fuels the biosphere. The sun evaporates an ocean's worth of water every 4,000 years. Technically, fossil fuels, too, are a form of solar energy, products of ancient photosynthesis. But as we all know, there's an unfortunate and ironic side effect to burning this archived sunshine. The emissions from fossil fuel combustion, especially carbon dioxide, but also nitrous oxides and soot, profoundly change the way the planet metabolizes the sunlight reaching Earth now. And of course, these archives are ultimately, and maybe thankfully, finite. In fact, trivial by geologic measures. The remaining economically recoverable fossil fuels in the world have an estimated total energy content of around 10 to the 23rd joules, equivalent to about a month of solar radiation reaching the Earth. Luckily, the forecast for the next few billion years is sunshine. A second lesson from the Earth: be loopy, dance endlessly around in circles. That is, recycle. Earth is basically a closed system. Other than a fine rain of comets and micrometeorites and the occasional dinosaur-killing asteroid, Earth has not acquired any significant new mass since it formed 4.5 billion years ago. Yet the median age of continental surface rocks is only about 500 million years. The oldest ocean crust is 170 million years old. The oceans are refreshed every few millennia. And as Hutton noted, soil is constantly washed to the sea, but so far hasn't disappeared. This means that everything on the planet is incessantly recycled, reforged, and restocked. The water, air, soil, the very crust of the Earth at vastly different rates via evaporation, precipitation, oxidation, reduction, subduction, metamorphism, melting, crystallization, erosion, and mountain building are reused, reacted, and remade. Every process has an inverse operation, every flow a compensatory counterflow in an intricate system of checks and balances. It's like an elaborate contradance happening across many spatial and time scales in which after many rounds, everybody ends up back where they started. In fact, this tendency for infinite repetition and reinvention is the single most important attribute that distinguishes Earth from its sister planets. It's not simply that Earth happened to be the right size and distance from the sun, but that it developed habits as a young planet that have kept its surface environment clement for most of the past 4 billion years. Life on Earth got involved in the circular logic early on. In the biosphere, commodities are by necessity used at rates commensurate with their abundance. If an essential element is very scarce, organisms have only a few options: learn to live with extremely limited amounts of the commodity, specialize in harvesting it from the environment, and/or find ways to recycle it for repeated use. Given that the alternative is extinction, organisms have come up with ingenious strategies to make a little go a long way. The biogeochemist Tyler Volk suggested that the frugality of biological systems can be quantified by what he calls a cycling ratio. It's the amount of a commodity that changes hands in an ecosystem divided by the amount that exits that biotic system in a given period of time. Essentially, the number of times that the element or molecule is traded between organisms before becoming locked up in sediment or returning to the atmosphere. A resource that is reused many times via transport between organisms, for example, soil microbes, plants, herbivores, carnivores, scavengers, decomposers, before leaving the biotic system will have a higher cycling ratio than one that is taken and discarded after a single use. The values of natural cycling ratios vary over many orders of magnitude depending on what systems and resources one's considering, but cycling ratios are always inversely correlated with availability. That is, the scarcer the resource, the more the biosphere will recycle it. So let's consider two elements needed by life forms. Calcium, used by calcifying organisms like these little coccolithophores to form shells and exoskeleton, and also by our own branch of the animal kingdom for bones. And nitrogen, essential for all life forms, from bacteria to buffalo at the cellular level. Of these, calcium is by far the more abundant in the Earth's crust. It represents between 2 and 10 weight% of average igneous rocks in the near surface, and has a pretty low cycling ratio, not quite 2. So calcium is akin to a disposable coffee cup, used once and sent to the landfill, except that in nature, even that which is discarded by the biosphere finds utility in the inorganic realm. In particular, calcium carbonate, or calcite, secreted by these organisms, most of them tiny, like these tiny coccoliths, accumulates to form limestone. And this is Earth's ingenious long-term carbon sequestration method. More about that in a minute. Nitrogen, which is virtually absent from rocks, is abundant in the atmosphere, but not in a form accessible to any organisms except for a few experts, highly specialized nitrogen-fixing microbes in the soil and the sea. Volk estimates that the global biological cycling ratio of nitrogen is more than 1,000. That is, the average atom of nitrogen is exchanged between organisms 1,000 times before exiting the biosphere. But as we know from the growing dead zones in the oceans, in the Gulf of Mexico, Chesapeake Bay, the Baltic Sea, and elsewhere, when organisms do have access to abundant nitrogen, they just can't control themselves. They gorge on it, and then, in decomposing, suck the oxygen out of the water, which in turn kills others, leading to more anoxia. Over geologic time, biogeochemical cycles evolved to be exquisitely balanced, elegantly choreographed, with all participants moving in stately synchrony. Our oafish alterations to them are something like driving a tractor into the contradance. It's sobering to note that all of the great mass extinction events of the geologic past have been linked with severe disturbances to the carbon and other biogeochemical cycles. Even the dinosaur extinction event, which of course is linked with the meteorite impact, was ultimately caused by ensuing upheavals in the chemistry of the oceans and the atmosphere. And the bedrock story of the greatest mass extinction in Earth's history, the end Permian cataclysm, tells how a thriving global biosphere was nearly dealt a mortal blow by the combined effects of abrupt, volcanically induced greenhouse warming, ocean acidification, and widespread marine anoxia, a scenario chillingly familiar to Anthropocene listeners. We have made small steps toward learning the biogeochemical contradance. These days, in most municipalities, recycling of containers and paper is mainstream, and that's a good thing, but it obscures an ugly truth. In this country, although we're recycling at a much higher percentage of our household waste, about 35% now, than we did in 1960, which was about 3%, the total amount of waste we generate each day has grown even faster. So depressingly, the yearly amount of per capita non-recycled waste has actually increased. Also, few manufactured goods attain cycling ratios of even 2, even though the components in them, like rare earth elements, are very scarce and environmentally damaging to extract. And too often recycling or even repair is not possible because gadgets like computers, cell phones, coffee makers, and so many others are not designed to be dismantled, and parts can neither be reused nor replaced. We used to get much higher cycling ratio scores. In frontier America, to be frugal and resourceful was a necessity, a virtue, the very heart of our national identity. Today, consumer spending is considered the best metric of the nation's health. And of course, the big elephant or element in the room is carbon, namely our non-looping, uncompensated one-way injection of it as CO2 into the atmosphere. An unjust fact about carbon emissions is that while one part of the world, the US, Canada, and Western Europe, have been responsible for a disproportionate share of the output over the past century, the whole world suffers the consequences. This is because the mixing time in the troposphere, the lower atmosphere, that's the time it takes for turbulence stirring by winds and weather to homogenize the air on a global scale, is relatively short, about a year, compared with the residence time of carbon in the atmosphere, which is about 100 years or more. If the mixing time were long compared with the residence time, then CO2 would hover close to the places where it was released, like garbage piling up when trash haulers strike, and might motivate action to emit less. But because our individual emissions are not only invisible but conveniently dispersed around the world, we have felt little incentive to curtail them. We've been living for a long time like the louche protagonist in Oscar Wilde's Picture of Dorian Gray, who, in spite of a reckless, narcissistic lifestyle of gluttony and drunkenness, as well as cruel and immoral behavior, mysteriously remained youthful and handsome for decades. In the end, his horrible secret is revealed. For years, a portrait of him he kept hidden in the attic had accumulated the effects of his debauchery, and when it is brought into the light, the full horror of his contemptible lifestyle is revealed. Now we're getting to that point with carbon emissions. Our first priority should be to cut emissions dramatically and immediately, but at the same time look for ways to put our carbon away, not in the attic, but the way nature does. Some pilot carbon sequestration technologies take their cue directly from the same quiet, underappreciated geologic process that Earth has used for years to manage CO2 exhalations from volcanoes, namely chemical weathering of calcium and magnesium-bearing igneous rocks that combined with CO2 in the form of new carbonate minerals like calcite, the principal component of limestone. And in simplified form, the equation that's on the upper left there encapsulate this. It's CO2 in the atmosphere reacts through water, rain, with an average crustal mineral, CaSiO3, and then in solution, those are carried to the sea, where some of it's picked up by silica-based organisms like sponges and diatoms, and then the rest is picked up by coccoliths and other calcifying organisms. This is the carbonate-silicate cycle over very long timescales. This is the thing that has kept Earth from becoming a runaway greenhouse planet like Venus. Unfortunately, in nature, this process, mediated by biological precipitation of calcite, is too slow to keep up with anthropogenic CO2 emissions, which now outpace those of volcanoes by a factor of more than 50. And in fact, as the oceans become more acidic, this mechanism is actually slowing down because it becomes harder for marine organisms like those tiny coccoliths to form shells as the pH of seawater falls. It may be possible, however, using a particularly reactive type of rock, magnesium-rich peridotite, to speed up the process of fixing carbon in mineral form at land-based sites. The catch is that although peridotite is very abundant in the Earth, it makes up most of the Earth's mantle, it's quite rare at Earth's surface. But there are places, including Newfoundland, Oman, Cyprus, and not that far from here, up in the Klamath Mountains, where past tectonic upheavals have thrust slabs of mantle rock up onto the edges of continents. It's an appealing idea that rock from the interior of the Earth could help us mend the damage we've done to the atmosphere. The problem, of course, is that transporting concentrated carbon dioxide, say from power plants, to the peridotite, the rare occurrences of it, or vice versa, would itself be an energy-intensive process. And while there have been some promising recent results from experiments in Iceland using basalt, which is a much more common rock type, even the most optimistic researchers emphasize that enhanced mineral sequestration of CO2 could never keep up with our still rising emissions. Other innovators are hoping to find scalable ways to capture diffuse CO2 directly from the atmosphere, but these are too expensive to implement as long as we can, in the manner of Dorian Gray, keep spewing out carbon for free, with no personal consequences. But the good news is that we already have the technology to capture CO2 directly from the air and simultaneously create a versatile building material. It's called trees. Photosynthesis is still the best bargain around for carbon capture. One last lesson from the geologic record, to adopt the mantra of economist E.F. Shoemaker: small is powerful. Gargantuan creatures and enormous calamities dominate popular depictions of the geologic past. Tyrannosaurs, woolly mammoths, megavolcanoes, and giant asteroids make for better entertainment than do photosynthesizing cyanobacteria and imperceptibly slow changes in the landscape. But the fact is, Earth's most dramatic topography is sculpted mainly by raindrops and snowflakes, and while hulking monsters have come and gone, microorganisms have survived, and in fact, been in charge the whole time. This is what I call microcracy, rule by the tiny. The modern science of geology actually began with the recognition of the might of the minute, the realization that Earth's surface was shaped not by biblical cataclysm, but rather by apparently inconsequential incremental processes integrated over space and time. This principle was also essential for Darwin's epiphany that the subtlest variations in the traits of organisms have given flower to the immense diversity of life. Although the inexorable workings of natural selection have led to some truly colossal beasts, it is in no sense hyperbolic to say that microbes, bacteria, algae, protozoa, fungi, viruses, govern the biosphere. They are the base of aquatic food chains. They are critical to the biogeochemical contradance, closing nutrient cycling loops by breaking down organic matter. They populate every conceivable environment on the planet and mediate the chemistry of soils, the oceans, and the atmosphere. They even eat rapaciously away at rocks. Acids produced by microorganisms accelerate chemical dissolution of rocks at Earth's surface by many orders of magnitude. If the metric of success is longevity, they are by far the most successful group of organisms. They appeared within a few million years, 100 million years of Earth's formation, and reigned alone for 3 billion years before macroscopic life forms showed up. When even larger creatures and their baroque ecosystems have repeatedly risen and fallen in evolutionary radiations and extinctions, microbes, simple, versatile, resourceful, have quietly persisted. We've employed them for centuries to make bread, cheese, and beer, but only recently come to appreciate the microbiomes in our own bodies, where there are more guest bacterial cells than native animal cells. Most of these are benign, and many are essential to digestion and healthy skin. But of course, there are also microbial villains. If anyone is skeptical that we live in a microcracy, consider that few modern humans worry about being eaten by large carnivores, but do fear measles, E. coli, HIV, MRSA, C. diff, and other Lilliputian adversaries. As formidable enemies or powerful allies, microorganisms teach us that tiny is not the equivalent of trivial. Although microcracy is ubiquitous in the natural world, there is something deeply counterintuitive about it, perhaps because evolution has programmed us to be more wary of large, fast-moving carnivores than slow, incremental threats to our existence. Or maybe it's because human societies too often vest power in the rich, the belligerent, the self-aggrandizing, and others at the top of the food chain. Microcracy is, in essence, the principle underlying democracy, but even in well-established republics, we struggle not to succumb to skepticism about whether our participation matters. We too often interpret the egalitarian dissemination of power as individual helplessness, despairing that our solitary actions or lone votes will have no effect on the environment or the outcome of an election. We forget that the potency of microcracies, whether bacterial or political, arises not simply from the sheer numbers of individuals, but from the networks of connectivity among them. Certain strains of bacteria and even some insects can coordinate their collective behavior via quorum sensing, biochemical signaling that allows a decentralized population to assess its own size and respond appropriately to its environment. Depending on the species and the setting, this can lead either to healthy guts and thriving ecosystems, or to cholera epidemics and plagues of locusts. The internet is the most obvious anthropological illustration of the potency and peril of a highly interconnected microcracy. It has empowered millions of ordinary people by providing access to libraries of information and connections to virtual communities around the globe. But it has also spawned new viral subcultures of hate, disinformation, crime, and exploitation. Microcracy, like democracy, does not guarantee good outcomes. In both systems, small changes can become magnified and lead either to prosperity or pathology. The key is to identify the good bacteria and find ways to nourish those live and active cultures. So these are just a few examples of the wise principles and cautionary tales from the rock record. For me, knowing the long story arc of the Earth enchants the world and enriches my experience of being alive in it now, by establishing a sense of kinship with other humans and with all denizens of this planet, past, present, and future. But this poly-temporal perspective is at odds with our long-cherished belief that we humans are exceptional, and with the more recent conviction that our time is somehow utterly disjunct and set apart from all other eras. In his contemplation of the paradoxes of modernity, French philosopher Bruno Latour has observed, "We humans have a peculiar propensity for understanding time that passes as if it were really abolishing the past behind it, and that we are separated from earlier times by epistemic ruptures so radical that nothing of the past survives." In the last decade, this feeling of estrangement from the past has become magnified by the embrace of disruption as an intrinsically good and necessary thing in commerce and culture. We admire those who move fast and break things. But this view of time as a scorched earth kind of process is itself an itself an epistemic rupture with the past, not to mention a dangerous delusion that leads to a variety of ills, including, in alphabetical order, angst, anomie, hubris, impatience, narcissism, neurosis, pettiness, spiritual malaise, and other maladies. Earlier civilizations had different and arguably more sophisticated perceptions of time. In most pre-modern cultures, the past hovered over the present. Ancestors were felt to be watching. Past and future generations were understood to be knitted into one fabric. The medieval Scandinavian worldview included the concept of Virt, loosely fate, or the power of the past to shape the present and future. Virt was embodied in the world tree Yggdrasil, which gives structure to all of time and space. It was maintained by the mysterious female Norns, who water it from an ancient and continuously replenishing well while reciting the Orlog, the eternal laws that hold up the world. In Ghanaian tradition, there's the concept of Sankofa, usually symbolized by a backward-looking bird and associated with the proverb, "It is not wrong to go back for that which you have forgotten." In other words, move forward, but remember the past. There's the Buddhist concept of sati, usually translated as mindfulness, but actually something closer to memory of the present, suggesting a subtler relationship with time. In these traditions and many others, the past, present, and future coexist and interact in ways much more nuanced than our simplistic linear view of time. In our culture, we tend to mistake technological prowess for wisdom. The people we call visionaries base their conceptions of the future on the notion that we should do everything in our power to circumvent the irksome constraints of the natural world that have shackled hapless denizens of the past, not appreciating that Earth is so much more powerful and more patient than we are and will always prevail. The idea that Earth time just doesn't apply to us leads to the delusion that we can outsmart the complex system of biogeochemical cycles and, for example, magically solve our climate woes through stratospheric sulfate injection, and expect that there won't be a powerful backlash of unintended consequences as the contra-dancers reorganize themselves. Disrespect for time also seduces us into thinking that we could skip over all that inefficient millions of years of coevolution stuff and just terraform ourselves another planet. Engineering the climate or terraforming Mars sound easy if you're completely unaware of the intrinsic timescales of geological and biological phenomena, the deep evolutionary pathways that gave rise to the world we live in, the intricately choreographed behind-the-scenes biogeochemical cycles, the housekeeping crew that make Earth habitable. Such ideas are beyond hubris, revealing not only a profound ignorance of the Earth, but also of human nature. What makes us think we could successfully change the rules that govern this or another planet when we haven't even learned to govern ourselves? Anthropologist Clifford Geertz famously defined culture as the constellation of stories that groups of humans tell themselves about their place and purpose in the world. In Western culture, with its Judeo-Christian underpinnings grafted to principles of social democracy and capitalism, the stories we share about who we are largely exclude the natural world. Nature is at most a passive backdrop, the scenery against which the real stories unfold, not a central protagonist in the narrative. Well, very soon now, that scenery is going to start directing the play. Long-term thinking is absolutely essential to grappling with the intractable issues of our time, whether it's climate change or intergenerational poverty. Yet just when the need for it is most acute, our attention spans are shrinking. The political and economic infrastructure we have has few mechanisms for sustained action over the timescales needed to resolve our most stubborn problems. Government is increasingly hamstrung by the 2-year congressional cycle, and corporate decision-making is yoked to shareholder demand for positive annual or even quarterly returns. As individuals, we hardly have time to look up from our phones. Meanwhile, our leaders embrace anti-scientific, magical thinking that makes medieval worldviews like Virt seem positively enlightened. And increasingly, the only institutions that can act on intergenerational timescales are authoritarian governments or foundations underwritten by the super wealthy. While the actions of many of these organizations are laudable, they are also fundamentally undemocratic. We need to re-democratize the future. When we peer into the geologic future, a paradox emerges. To some extent, we can see what lies in the far distance more clearly than what is in the foreground. The sun, as a G-type star, is about halfway through its lifespan. And in 5 billion years or so, we'll enter its red giant phase, engulfing the Earth and the inner planets. 3 billion years before that, however, the sun's increasing luminosity will lead to an extreme greenhouse effect from the vaporization of Earth's oceans. Once the planet's water has been lost to space, the carbonate silicate weathering system that has acted to sequester volcanic CO2 over geologic time will shut down, creating an even more intense greenhouse state that would likely make surface conditions intolerable for all life about 2 billion years from now. For at least the next billion years or so, plate tectonics will continue to shuttle continents to new positions on the globe. The Atlantic Ocean will begin to close, and in about 250 million years, the Americas will be reunited with Europe and Asia in a new supercontinent that has already been named Pangaea Ultima. Meanwhile, rivers will have erased the Himalaya, Alps, and Rockies. In about 80,000 years, the Earth will reach the point in its orbital cycles where another ice age could happen, but this will depend on greenhouse gas concentrations, ocean circulation, the state of the biosphere, and many other variables. The next 1,000 years, the same amount of time that separates us from the Viking Age, are even harder to bring into focus. If human emissions of carbon have not sharply been curbed and powerful positive feedbacks in the climate system are activated, the Earth could experience a replay of the Paleocene-Eocene thermal maximum 55 million years ago. Temperatures would spike by 8 to 10 degrees, marine and land-based ecosystems would be stressed to the point of collapse, sea level would rise tens of feet, inundating most of the world's most populous cities. Altered weather patterns, more ferocious storms, longer and deeper droughts would stress world food production, increasing proportions of government budgets that would have to be channeled into crisis management. The balance of geopolitical power would shift depending on how nations fare in the new climate regime. But none of this is preordained. We have the power to write a different saga for the coming millennium. Rather than lapse into existential despair that we won't be here in a billion years, let us reclaim at least the next few centuries. It is empowering, or at least therapeutic, in these dark times, to imagine what a time-literate society might look like. In his last public interview, Kurt Vonnegut said, "I'll tell you, one thing no cabinet has ever had is a secretary of the future, and there are no plans at all for my grandchildren and my great-grandchildren." Let us adopt Vonnegut's suggestion as our first proposal, a representative for the yet-to-be-born to serve among the top advisors to the president. The Department of the Future would set in motion a realignment of priorities in all aspects of society. And now we should cue some triumphant music, I think. The secretary will declare some new national holidays, Aldo Leopold, Rachel Carson, or Chief Seattle Days to honor great long-term thinkers. Photosynthesis and Carbonate Rock Week, a time to celebrate the mighty legions of coccolithophores and others who have kept the planet from becoming a runaway greenhouse. Resource conservation would again become a core value and patriotic virtue. Tax incentives and subsidies would be rebalanced toward rewarding long-term stewardship over short-term exploitation. Putting a price on carbon will help us get a grip on our fossil fuel addiction, sober up, and let us prepare for the natural disasters that will happen without our assistance, like the hundreds of large earthquakes that will happen around the globe in the next century, rather than expending resources on self-created climate catastrophes. Poverty and class-based disparity of opportunity would be recognized as problems with deep historical roots that cannot be solved without sustained commitment over commensurate timescales into the future. Public school teachers and others whose work represents an investment in the future would be paid well and held in high esteem. Geology would be fully integrated into science curricula, perhaps serving as a capstone course in which students would apply physics, chemistry, and biology to the immensely complex Earth system. With a solid understanding of how the planet works, students would go on to become educated voters who would hold public officials accountable for wise governance of water, land, and air. Legislators, governors, and mayors who embrace the seven-generation principle would point proudly to what they are doing and be re-elected by grateful constituents. More generally, schools would help develop children's knowledge of and appetite for history and natural history, instilling in them a deep instinct for their place in time and a keen curiosity to understand more. The dramatic narratives of the geologic past are perfectly suited to the human appetite for storytelling. Like many who experienced childhood or parenthood in the last 50 years, I love Maurice Sendak's Where the Wild Things Are. It's a book about the power of imagination to take us to other worlds, transcend time, and save us from our worst selves. I think of Max's Voyage whenever I teach History of Earth and Life, a course in which we cover Earth's 4.5 billion year history in a 10-week term at an average clip of about 450 million years a week. I always feel that I've been on a long journey with my students. We've witnessed alien Earths, explored alternate ecosystems teeming with strange wild things through bountiful times and bad ones. Finally, we approach the present and see the modern world emerging from the mists, just as Max's room gradually sheds its vines and becomes recognizable again. I believe, perhaps naively, that if more people could experience this journey and see themselves as Earthlings with a common past and shared destiny, it might spring us out of our polarized and entrenched ways of thinking about the world. As a geologist, I've worked with people from all over the world, from very different cultures and generations, older and younger than mine. The strong human connections I've developed with them through our shared study of Earth make me optimistic that a geocentric, timeful worldview might help us overcome the animosities and barriers that divide us and get down to work on things that really matter. Collective awareness of Earth's story might save us from environmental hubris. Understanding how historical happenstance is written into each of our personal lives might cause us to treat each other with more empathy. And a timeful habit of mind might even make us less neurotic about the fact of our own mortality by shifting our focus from the finite lengths of our lives to the rich anthology of experiences that a lifetime represents. While other senses may be dulled with age, the sense of time, which can only be developed by experiencing it, is heightened. Growing old requires one to shed the illusion that there's only one version of the world. As Darwin wrote on the last page of Origin of Species, in a sentence, I will warn you, with many commas and a semicolon also, there is grandeur in this view of life, with its several powers, having been originally breathed into a few forms or into one. And that whilst this planet has gone on cycling according to the fixed law of gravity, from so simple a beginning, endless forms, most beautiful and most wonderful, have been and are being evolved. That grandeur has always included us. We have simply tormented ourselves with the idea that we are outside the garden. As a technological society, we have an almost autistic relationship with the Earth. We are rigid in our habits, savants when it comes to certain narrow obsessions, but dysfunctional in many other regards because we wrongly view ourselves as alone in the cosmos. Believing that nature is something outside us, a mute and immutable thing external to us, we are unable to empathize or communicate with it. But the Earth is whispering in our ears all the time. In every stone, it offers an eternal truth or a good rule of thumb. In every leaf, a prototype power station. In every ecosystem, a model of good urban planning. In every watershed, an exemplar of a healthy economy. We need to view ourselves not as consumers or members of political tribes, but citizens of Earth, this still evolving tangle of old, recycled, sun-powered, and profoundly interdependent dancing parts. There's a teaching attributed to the 18th century Polish Hasidic rabbi Simcha Bunim that for me, a very lapsed, indeed deeply agnostic Scandinavian Lutheran, carries great wisdom. One should carry 2 slips of paper, one in your left pocket reading, "I am ashes and dust," the other in the right reading, "The world was made for me." Both are true. Somewhere between the poles of existential despair and narcissistic self-absorption lies the path that will take us back to the center of the cosmos. But our Holocene snow day is ending now, and no one is going to be waiting for us with a warm supper. It's time to grow up, and with a clear-eyed view of both past and future, resolve to become better ancestors and start making up for so much lost time.
Thank you so much. Well, you can all kind of get a sense of how this lines up with the long now way of thinking, I think, so perfectly. And I think the thing that struck me more than any other thing was how closely tied massive lengths of time in the geologic sense were tied to, that you kind of, every chapter tied to much everyday kind of human interactions. And I think the one that struck me the most is the idea that Darwin, of the few books he had with him on the Beagle, was
Principles of Geology by Lyell. Yeah.
Right. I wonder if you could talk a little bit more about that, which I thought it's interesting that he was so influenced by geology.
Yeah, so I guess I didn't mention Lyell in the talk, but he is considered one of these patriarchs, along with Hutton, of geology, and really wrote the first treatise, modern treatise in geology. It was called Principles of Geology. It was 3 volumes, and the first volume had been published by the time that Darwin went on the voyage of the Beagle, and he only had, I don't know, a small box of books with him, so he studied it in great detail, and it tremendously influenced him consciously and subconsciously about the power of small incremental changes to accrue over time and accomplish large transformation. So that,
and
that's
itself kind of a heretical book in the sense of the Christian sense of time.
Right, but Lyell was a really very astute rhetorician. He was a lawyer by training, and the book is written in this kind of florid way. He made a fairly bright line between the evolution of the physical world and humans. He elided the possibility that maybe humans had just emerged from physical processes. So it wasn't really until paleontology matured a little bit more in the 1840s and 50s, and then Darwin, of course, publishing Origin of Species, that geology and the church began to be at loggerheads with each other.
And this, the idea of rocks as verbs, that, I mean, really what they are kind of storytellers, that if you just kind of need to find the right key to unlock them. And we were talking earlier about an event that happens near where you study, a mere 1.85 billion years ago on a very single day. But I wonder if you could elaborate a little bit about that.
Right, yeah. So
that
geology, Wisconsin, where I live, is not perhaps perceived by many people as a mecca for geological expeditions. But we have a lot of really interesting old rocks. And one of the most remarkable discoveries in the last 10 or so years has been the ejecta layer from the impact at Sudbury, Ontario, which has been known as an impact crater. It's actually the second largest impact crater on Earth that's still preserved. But no one had thought to look for the ejecta till about 10 or 15 years ago, when a high school teacher from Thunder Bay, who was fascinated with the KT boundary story, the dinosaur extinction story, said, hey, the rocks in our backyard, 500 miles from Sudbury, are just the right age. We should start looking for the ejecta layer. And once we narrowed down the horizon that people should start to look, indeed they did find it. Shocked quartz, crazy looking rocks thrown up by a tsunami or something that was caused by the impact. And it's one day, 1.85 billion years ago, that we can trace almost all around the shores of Lake Superior now.
Yeah, no, it's fun. It's such an amazing story. And your book is kind of replete with these stories of each site that people visit kind of has some version of these stories, whether it's a coring of the Earth in a site or a place where the Earth is exposed. And you were studying in Svalbard, and what were those rocks telling you?
So they're records of the northernmost extension of the Appalachian Caledonide chain that runs from southern U.S. up into the maritime provinces in Canada, and then Greenland and Norway, and then up into the Arctic region. So just trying to reconstruct exactly where the plates that built Pangaea were at that time.
And Liz Voller asks, as a geologist thinking about timefulness, how do you think about spaciousness or spacefulness?
Well, I guess I think geologists, especially in the pre-digital age, had to learn to really create mental maps. When we were working, for example, in Svalbard, we did not actually have very good maps. We mainly mapped on air photos that had been taken in the 1950s, and often the glaciers were in a very different place. So you learn early on as a geologist to kind of create mental maps of wherever you are. So I would say I think I'm spaceful, and I think most geologists are placeful, because you can't bring the rocks to you. You have to go out to the rocks, and so you have this sense of geography in space and time. They're tangled up with each other.
And it sounds like you have a more nuanced and I think, appreciative view of what it might take to re-geoengineer ourselves out of the situation that we have clearly kind of geoengineered haplessly into. But you also mentioned some of these naturally occurring elements or minerals that could be helpful, and I wasn't exactly sure how those connect.
Right, and I know you've had David Keith here talking
Yes.
about. I'm a big skeptic, and I think it's a dangerously easy idea to do the stratospheric sulfate injection into the stratosphere without fully understanding what we're in for, and we don't have any international governance mechanism for that. But I do think perhaps some geomimicry of Earth's long-term carbon sequestration project, which is limestone, might be a good idea. It is not likely to have ripple effects. It's just that we don't have a way of bringing the CO2 and the rocks that are going to react to do that together easily yet.
So would that be used in scrubbers, or so you would mine it and use it at the source? Or?
Yeah, I mean, so first of all, you would need clean coal, or you'd need some way of sequestering concentrated CO2 and then delivering that to places that have either peridotite, which is pretty rare, the mantle rock I was talking about, or basalt, which is not all that rare, but still, usually you have not built a power plant because of the bedrock underneath it.
Right.
So I am not holding my breath that this is going to be the solution, but there are some promising experiments, as I said, in Iceland, where the whole place is basalt.
Right.
And they also have higher temperatures because of the volcanic activity there, and the kinetics of the reactions at those temperatures was pretty fast, and they were able to sequester a fair amount of carbon in a short period of time. But again, the geography is the problem, getting concentrated CO2 to the rocks that will react. So it's...
And so, and just the mechanism of that reaction, is that by exposing those rocks? So it would be some kind of mining operation that would...
Or injecting into wells.
Gotcha, okay.
Yeah, that's I think what most people are thinking, not mining the rocks,
right,
but perforating them.
And then bringing the CO2 there.
Mm-hmm.
Gotcha.
Yeah.
Kevin Kelly asks that some forecast climate change happening a significant degree in 20 years, others claim it will take centuries. Can geological change happen in decades? Is this an error of timescales?
Well, that's a good question, because our resolution, especially as we look farther and farther back in the geologic record, becomes fuzzier. But we can look at ice core records where, at least for tens of thousands of years, we have near annual resolution. It gets less as the ice gets very compressed and diffusion between layers happens a little bit. But there we can see annual to decadal and certainly century timescales, and sometimes change is very abrupt. So when we talk about some of the great mass extinction events, then the denominator, this much extinction in so many years, gets harder to discern because our dating techniques don't have that kind of precision. But for more recent and arguably more relevant climate change, we can say, yeah, sometimes things happen pretty fast, often in response to changes in ocean circulation. That can happen on certainly human-like timescales.
Mm-hmm. And another question from the audience. Are petroleums being created now? Mm-hmm. Or is this only a case of something that could have happened in a specific era, like I think you mentioned, I don't know if you, in tonight's talk, I don't think you mentioned the great oxidization event, where kind of all of our iron was created in one
That's
time.
Right.
But we mine for petroleum in one chronologic layer.
Sort of, yeah. So petroleum is being created very slowly by microorganisms raining to the seafloor and then becoming buried and then undergoing partial decomposition, but not in a way that would allow us to tap into the oil and gas that's being created now. Most of the great oil fields around the world happen to be Cretaceous age, probably the majority, simply because that was a time of very high sea level, and most petroleum is accumulating in the shallow continental shelf areas. And when you have higher sea level, you have bigger continental shelves. And it was a time of very high marine productivity as well. But yeah, fossil fuels are still accumulating slowly.
Just at a much slower rate than we happen to be burning, yes. There was a topic that came up in your book as well that I was really interested in. It was a game called Cooperating with the Future. I was wondering if you could talk a little bit about that?
Yeah, now I have to think exact. I don't remember the organization. It was an academic paper
I don't know if I wrote it down here. Yes.
where people were allowed in different scenarios to make decisions about how to use or allocate a resource that could be depleted. And they found, not surprisingly, that if there were really kind of no incentives for cooperation, the tragedy of the commons would happen over and over again, in which one bad player would take his or her more than his or her share, and everybody lost in the end. But they experimented with different sort of cooperative strategies, and they found that in groups, if people could kind of collectively decide on what was a reasonable take for each player in a given period of time, that was a way of kind of restraining each of the players. And I don't remember exactly the details, frankly. But I think some of this game theory and experiment with building in checks and balances that mimic those in nature, where it's just not possible for any one organism or one species to take it all, is the way to go, that everyone benefits from some mutual restraint.
It comes back to another question that Ken Brode had here that about world governance, and I think you mentioned this in geoengineering. You kind of need it in this economic model as well. You mention it in your kind of, I think you called it a chronotopia, which you explained here at the end of your talk. A world in which is so immured with time that that we take it so seriously that all of these things kind of work out in this sense. Do you see any moves towards our world government?
Well, I'm a geologist. I feel in my bones, and I go to work every day because I do think education is part of it. That just having a better sense of the stories of the natural world will reach people. It's part of the solution, it's not the whole solution. We need economic and technological and governmental mechanisms as well, but education is part of it, and that's what I do. So I remain optimistic.
We're not going to leave you on the hook for building the next world government. And Kevin Kelly actually had a follow-on question to the one about are we creating petroleums now? But and I've heard this theory as well from Danny Hillis, one of our other founders, that that petroleum may not be so much from dead plants, but from a geochemical process. Do you find there's any value to this?
I don't think they're mutually exclusive. I guess I would say, and I'm not in the petroleum industry, but we can look at some of the organic compounds, and we can see a continuum. You know, if you bake phytoplankton at a certain temperature over a period of time, you see biochemical markers that certainly are consistent with their origins from biogenic sources. But there are many things we don't understand about the way the Earth works yet, and I would not deny the possibility that in some cases we're getting these organic compounds generated in other ways.
Or an interplay between the two.
Or, yeah, exactly.
And I think back to your thoughts on how we create or mimic the systems of these kind of recycling systems that the Earth has. One of the questions here...
Which, let me just say, Jim Lovelock, happy birthday.
Yes, yes, indeed.
Because that's really his view of the Earth as this just amazing amalgam. We call it biogeochemistry, not Gaia, but that's really what we're talking about.
Right.
Yeah.
Is that, basically that maybe we really underappreciate our waste, and that our problem is not so much that we're creating waste, but we haven't created the right cycles the way that nature has. Does that kind of fit with those views?
Yeah, and just consuming way too much anyway. Accelerating some of the processes that do happen in nature by orders of magnitude. It's just impossible to find ways to have compensating counterflows as we do in nature. It's just the magnitude of our activities is too large. And
I think Angus McGrath talks a little bit about the idea of, we seem to be able to grasp the fact that our lives and that of our children and grandchildren can be 200 plus years, yet we seem to only be rewarding these vastly shorter timescales, even though we we do have value in that future in some way. And I think, do you have some sense of what's holding us back from being able to act in this way?
I mean, we blame our evolutionary roots that we aren't programmed, hardwired to be able to think past our next meal. But come on, we've achieved so many other things. Why can't we find the self-restraint and political will to act on what we say our values are? I don't know.
Well, I think you touched on it a little bit with the ideas behind, I think, Samuel Scheffler in the book, where this idea that if we didn't think that there was a future to hand the world off to, we would actually act radically different than we did. It would be a very hopeless time. So we sort of act that way, but we still have this kind of strange hope that the future will either fix it or deal with it. Can you explain a little bit more about Scheffler's ideas?
Yeah, so he's a philosopher, I think at Swarthmore, I'm not sure, but he provocatively has pointed out that psychologically we count on future generations coming after us. It would be a terrifying thing to think that we are the last. And I think there was a movie, Children of God, that was based on P.D. James' novel. That's sort of the premise. And so we owe future generations our sanity, arguably. And so we probably owe them something in return. I mean, our sanity is due to them, so we should do the best we can to take care of them because they are keeping us from going insane.
Yeah, well, that's an interesting way to put it. It's a different way of being a good ancestor, yes. And Jessie Kate Shingler asks, on a universal geologic timescale, how might we think about or define sustainability of humanity as we become a multiplanetary species? Sounds like you're dubious of our multiplanetarianness.
I am. So I don't know how to answer the question quite in the context. I do think it is naive of us to imagine that in a few generations, first of all, that we could cooperate enough together to actually transform, say, Mars, which seems the best prospect, into anything like a hospitable place without so much high-tech intervention that it's not really going to be relevant to the most of the rest of the population of Earth. Because of my understanding of the way the Earth's system has evolved. Earth has not been the same through all of its history. I think that's one thing that has changed in my time as a geologist, of 30 years or so. We see that Earth's story is kind of a Bildungsroman. It's a developmental story. And Earth has had many different modes. Certainly the biggest biogeochemical change was the great oxygenation event that happened about 1.85 billion years ago, where we went from an atmosphere that was probably mostly CO2 and water vapor to one that at least had some free oxygen, not 21% like we do now, but some, which changed all the biogeochemical rules. And then there was a second jump only about 600 million years ago to something like near modern values. So there are really different chapters in Earth's story. And maybe that could be sped up a little bit on another planet. But, I mean, the timescales here are large. And we don't even know all the players involved. We have only a tiny fraction of the microbes in the world classified and understood in terms of their metabolisms and what they're doing for us behind the scenes. So I just find it very naive to think that we're going to be able to go to another planet and manage biogeochemistry on that scale. Yeah.
Do you think going there and I agree with you. I think though that there's even value in going and failing. That the showing of the difficulty in a way, if a few humans get there and they can barely survive and pretty much have to vacate or can only survive from massive influxes of energy from Earth and supplies.
I would argue we can do that with modeling.
Well, we can, but I don't think it changes the global perception, right? Like, so it's. I think one of the things we're talking about is changing global perception, and I think there's all kinds of things that happen from exploration that are beneficial, I think, to humanity, that are intangible in other ways that going
I'd like
to
to
Mars.
see the price tag and see whether we could put that same amount of money toward other
The
other
Nobel
efforts.
for
And
geology.
there was the Biosphere 2. People may remember this from the early 1990s, this closed ecosystem, or allegedly closed, in the Arizona desert, where maybe it was the scale, it was too small, but even on that scale, with everything quantified and inventoried very well, they were not able to control the oxygen levels, and finally had to open the place up because the people were getting really cranky and irritable with each other because they were getting only 14% oxygen, and the problem was that there was too rich soil in the agricultural sector of the Biosphere 2. And even though people had tried to calculate exactly how much CO2 that soil would be respiring, they were way off. And within a couple of, I think it was closed for about 8 months, but they had to open it up because people
Right.
were just unable to function. They had altitude sickness essentially the whole time.
Right.
Yeah.
Yes, I mean,
So,
I think
don't
these
know.
experiments are. I think these experiments are helpful for humanity because I think
They're
a
humbling.
model is a model, but watching humans suffer is a little bit different, and probably will capture imaginations a little bit better.
Yeah.
And as a last question, Kevin Kelly, really, you put a lot of questions in here. Thank you. What is the current geological heresy that you suspect may be true?
Ooh. So geologic heresy, something that...
Some theory of geologicness
Oh, that's
that might be
a
fringe now
wild
that you
thing people
think
propose?
has legs.
Ooh, I might need to think about that one for a while. Maybe the deep hot biosphere, the idea that there is, more microbial life living at depth than we think. That might be, again, I'm open to that idea. In my own field, people are recognizing that there may actually be another mode that Earth recycles crust other than subduction. This is kind of controversial.
Say that
it's
again?
called a different way that Earth's crust is recycled besides subduction, which has been the kind of paradigm since 1965 with the plate tectonic revolution. There's some evidence beneath the Himalaya that there's something people are calling drip tectonics, which is not really a very nice name, but where you have a big, thick pile of continental crust, the pressure can cause the bottom of that to become very dense metamorphic rock that can just fall into the mantle. And I remember people proposing this maybe 15 or 20 years ago, and now we have better geophysical methods for seeing what's going on in the mantle, and it's looking like maybe that's a real thing. So I don't know if other people care about that, but I think it's interesting. It was a harebrained idea people had, and now people are coming back to it.
Cool.
So,
And do you have other things in your future, other books, other projects?
maybe.
Yeah.
I do have a day job, and so it's hard for me to find time, but I realize that, again, I think there are many people, many earthlings, who really do have an appetite for understanding and haven't had the chance to take college classes in geology, so if there's an audience, I might try my hand at another book.
Well, your writing, I think, is some of the most evocative and, I think, human-scaled writing to geology since James McPhee that I read, and it's been amazing to find such a compatriot of long-term thinking in reading your book and now meeting you. Thank you very, very much.
Thank you so much, Brandon.